Hello and welcome to ECE 391 at the University of Illinois at Urbana-Champaign. Today we're going to be talking about the contents of the course and taking a look at the material in the course in three different ways. The first will be just the learning objectives of the course, what I'd like you to take away from this semester. The second will be a topic-by-topic overview, the big picture of what you'll be learning and the materials for the course. And then finally, I want to give you an idea of the elements and style of the course, so in particular what kinds of assignments you'll be doing and how those will help you achieve the learning objectives. So let's start with the learning objectives. These break into two categories. The first is knowledge, and the second is skills. So on this slide, you see the knowledge objectives. The first is to understand the hardware-software interface. So how the software running on a processor today interacts with the hardware devices such as mice, keyboards, disk drives, monitors, how that actually works. So I want you to understand that, and that's one of the big learning objectives for the course. The second is for you to understand how one abstracts physical resources in software. Now that's typically a problem that is the domain of the operating system. So the operating system allows your program to have a simpler view of the hardware that's actually connected to your processor. You might wonder, well, why do I want to study operating systems? Why is that an important thing for me to learn? And the first answer is, well, operating systems at some level are the epitome of all software. If anyone has ever had an idea, a technique, an approach that they've wanted to try out in software, often someone else maybe, but someone will take that idea and put that into some operating system. And so the operating system in that sense is something where you can see a lot of the ideas people have come up with over the last few decades. You can see those actually realized and used. And so we'll look at an operating system and understand a lot of the software techniques that people have developed. The second reason is that today there's an increasing abstraction level of embedded systems. So this is my phone. It's not a smartphone. It's kind of an old phone. It's not actually running an operating system, but your phone probably is. 5 years ago, your phone probably wasn't. It was probably more like this, not running an operating system. Today, the processors in your automobile are probably not running operating systems. In 5 years, all of them probably will be. As we move forward, more and more embedded systems are using operating systems, and for that reason, it's important that everyone who's going to work in electrical and computer engineering actually have some understanding of what the operating system is, what it does, how it controls the interactions between hardware and software. So that's the second goal for the course. The other learning objectives for the course involve skills. The first, learn to use tools. Tools are your friends. You'll be happy. There are a few examples here. So you're going to be working, for example, with the Linux operating system, 100,000 files. It's nice, after you've been modifying a few of those files, not to have to say, well, which ones did I change? Let me make sure I go type all the compile lines for each of those. Instead, you have the computer keep track of which files changed, figure it out, recompile all of them, rebuild that into the operating system image, and that is something that a computer can manage pretty nicely. That's a dependency management tool. Another example is source control. Source control allows you to do things like, oh no, I just deleted my file after 4 hours in the lab, 10 hours. And so what source control will allow you to do is get a copy from a repository where you've kept a copy of the last version of your working code, for example. It also will help you share code modifications with your teammates. So for example, if two of you have modified the same file, it'd be nice if you didn't have to sit and look by hand and try to make the changes that one of you made to the other one's file. Source control can bring those two files together and automatically, to the extent it's possible for the computer to understand what you were trying to do, merge them together. So that's another advantage of a tool like source control. The other big skill in this class is to practice team-based development and testing. Now it's important in industry that you learn teamwork skills. This is something our alumni constantly bring up with us, that our students need to learn how to function as part of a team. Many years ago, probably 20 years ago, you could find examples of heroic effort. A single person, actually, if you look at, for example, Wolfenstein 3D, that was really one person going and writing the 3D graphics engine 20 years ago. Today, that kind of thing never really happens in the software industry. Generally speaking, you're going to be working with a team, and you need to learn the skills necessary for teamwork. Now, the team focus in this class will be that for half a semester, you're going to be building an operating system on your own with your team of 4 people. So you'll be part of a team of 4 that builds an operating system from the ground up. So you really will learn to understand what it means for hardware and software interactions inside the operating system, and you'll learn the team skills through this team project. For example, you'll learn to communicate with your teammates, you'll learn to leverage individual strengths. One person might be a better programmer, another person might be better at coming up with clean interfaces, clean documentation, being able to relate to the other teammates, well, exactly how is this working, or even debugging. Figure out what your strengths are and leverage the strengths of the individuals in the team. That's part of being a good team player. And finally, designing workable interfaces. If you want to sit down separately and be able to write parts of the big system, you need to be able to first think through, well, what are the interfaces? What are the software interfaces between these parts, and design this cleanly and effectively? And that's another team skill. So the second part of today's lecture then will be to think through and look at the topics in the course. So I call this the big picture. We'll start with a new processor, new ISA for most of you. That'll be the x86 ISA. We'll give you a RISC-like or reduced instruction set computing overview of the design. So we're not going to cover some of the more advanced features of the processor, but we'll give you a nice overview of the ISA. Here, this picture has some memory connected to the processor as well as a program running on it. So we'll introduce the ISA and allow you to write some code with it to interact with a real-time clock inside Linux, and that'll take about a week and a half. So that'll be the first part of our course. We'll move on. We will talk about the interactions between hardware and software. In particular, we want you to understand how you deal with the asynchronous interactions between the hardware, things like keyboards, monitors, disk drives, mice, and the software running on the processor. That's usually through something called a programmable interrupt controller. Why is that necessary? So if you think about a processor today, processors are typically gigahertz, and so that means a few nanoseconds per instruction, or a nanosecond per instruction even. On the other hand, even a fast human typist might type at a rate of 100 words per minute. That translates to 1 character every 1/10 of a second. So clearly there's no reason for a keyboard to have a gigahertz clock on it. And in order for you to manage the interactions, you need to understand that these two systems are running at far different rates, and they're going to interact asynchronously. So when a key is pressed, how does your program, or the operating system actually, how does it deal with this asynchronous interaction? We'll spend about 1/3 of the course, or 5 weeks, on that topic. The next step then will be virtualization. Virtualization means providing the illusion of a large or even infinite number of resources, even though you've got a finite number of resources in your real system. So for example, in today's desktops or laptops, even today's phones, you probably have multiple cores. If you bought your phone in the last year, you've got multiple processors in there. If you bought it a couple of years ago, you don't. However, you don't have many, right? Nevertheless, for many years now, you've been able to run 10, 15, 20 programs at a time on your computer, and it seems as though all of them have their own computer. Now that, of course, is not really true, but that's what we mean by virtualization. How do you provide the illusion that you've got many processors in your system, even if you've got only a handful? So we'll start with virtualizing the processor. That'll take us about 1.5 weeks of the course. In the next step, we'll talk about virtualization of memory. So physical memory in a system today might be about 4 or 8 gigabytes, but you might be able to run something with, or 1 or 2 gigabytes in many systems still, but you might be able to run a program or a set of programs that require 4, 8, 16 gigabytes. How does that actually work? We'll spend a couple of weeks talking about how memory is virtualized. The next part of the course will be a discussion of how we abstract devices to provide simpler interfaces to the software, to the programs and applications. Let me give you an example. When you write your program and you say, oh, have the user type their name in at the keyboard, usually you expect your program to simply wait for them to type. But you know that the human typist is not going to type at the speed of the processor, and so the device drivers actually provides this abstraction so that your program doesn't have to understand the asynchronous interactions between the hardware and the software. We'll talk about device drivers for about 2.5 weeks. The next step is then to move on to user-level interrupts, or what are often called signals. We'll spend about a week on that. That's actually the ability to expose, even though most of the interfaces from the operating system will hide the asynchronous interaction, that's exposing it back to the software that wants to know about it. So let's take our example of waiting for the user to type in their name. What happens if instead you're writing a server and you've got 100 people connected to it and each of them is typing their name? When one finishes, you'd like to move ahead with responding to them. So if, for example, their name is Alice, you'd like to say, well, hello, Alice. Now, clearly your program can't wait for the next person, Bob, to be typing in his name when it's supposed to be responding to Alice, and so you need to be able to have the asynchronous interaction with some programs like servers. We'll talk about that for about a week and show you how the mechanisms work within the operating system. And then the last part of the course will be the file systems discussion. So you can see here that they fit in above the device drivers, and the kinds of things we'll talk about. Disk drives, the access times are about 10 to 20 milliseconds. And so we need to hide the fact that they take a long time to get to from the processor and think about how we cache information, how we manage information. There's a bit of reliability. So if we lose a block in the file system, we don't want to lose all of our data. If the computer turns off in the middle of writing to the disk, what happens? How do we shut down cleanly? So that's an overview of the class in 7 pieces. And the next thing I want to talk with you about is the elements and style of the class. So here's the last piece for today, is the third view of the class, the elements and style. First part of the class is, of course, the lectures. Here I'll offer you some practical advice as well as just go over the conceptual material with you. You'll also have labs, 4 of them. Here you'll get some hands-on experience with the tools and the real system. So you'll actually be able to apply what we're talking about in the lectures and integrate it and internalize it a little more effectively by learning and getting this hands-on experience. We'll also do pre-labs. The pre-labs will often involve you going off to the internet, gathering information that will help you complete your lab assignments. And so those will alternate. We'll go back and forth to a pre-lab and then a lab and a pre-lab and a lab. The last piece of the course then will be the examinations. We'll have 2 midterms and a final. With this class, there's a lot of importance in the lab. As I mentioned, it's a hand-on experience, and that's really where you'll learn a lot of what you're going to take away from the class. So there will be some emphasis during the exams on the lab material, but then also some emphasis on the concepts that we're teaching in the lectures. So we'll try to balance those two in the 3 exams that we take. So that's it for today. I've given you 3 views of the material. The first is just the learning objectives, the knowledge and skills that I want you to take away from the class. The second was the topical overview, the big picture for the class. And then finally, how the class breaks down in terms of the different activities you'll be doing. So thank you, and I'll see you next time.